Hello friends, so today we are going to solve the questions from the year 2016, and from the year 2016 we are having two main questions and two are from advanced. From the year 2017 we are having three questions from the mains and one question from advanced. And 2018 we are having two questions from mains and three questions from advanced. Therefore, total we are going to solve 13 questions. So first question, it was asked in the year 2016 mains, and it states that a combination of capacitors is set up as shown in the figure. The magnitude of electric field due to a point charge Q having a charge equal to the sum of charges on the 4 microfarad and 9 microfarad capacitors at a point distant 30 meters away from it would be equal to. So here we are supposed to find out an electric field, and due to a point charge whose charge is given as Q. So let us suppose this is a point charge Q, and we are supposed to find out the electric field at a distance. That distance is a 30 meter from this point charge, and the charge on this point charge, that is the value of Q, is given as sum of the charges on 4 microfarad as well as 9 microfarad. So you can say that that is equal to Q on 4 microfarad plus charge on 9 microfarad. Okay. So this we are going to find out charge on 4 microfarad and charge on 9 microfarad. We are going to add them. That will be giving us the charge Q, and then we can use the normal formula to find out the electric field. Okay. So first of all, we have to solve the given circuit. Okay. And from this circuit, we can clearly see that we have 3 microfarad and 9 microfarad are parallel with each other, and their combination will be in series with 4 microfarad. Okay. We are not interested in 2 microfarad because the voltage drop across 2 microfarad, because 2 microfarad is parallel with the supply voltage, let us suppose that is given as E, and the series and parallel combination which will be giving us some individual 1 capacitors will be also parallel with this. So we can easily find out the voltage. Okay, and that is going to give us a charge. Okay, so we are not interested in this 2 microfarad. We are only interested in this 4 microfarad and a parallel combination of 3 and 9 microfarad. So we can just draw them separately. So we have a 4 microfarad, and in parallel there are 2 capacitors. One is our 3 microfarad, 9 microfarad, and this is 4 microfarad. So let us assume the parallel combination of 3 and 9 microfarad is given as Cp. So we can say that the value of Cp will be equal to 3 microfarad plus 9 microfarad, which gives us 12 microfarad. So once again, we can just redraw the circuit, and we have a 4 microfarad capacitor, and then we have this as 12 microfarad capacitors. Both of them are in series. So in series, let us assume we call the series combination as CS. So we can say 1 upon CS is equal to 1 upon 4 plus 1 upon 12. So from here, we are going to get that our series combination, that is CS, will be equal to 3 microfarad. So finally, we get one individual capacitor, that is our 3 microfarad, and this is in parallel with 2 microfarad capacitor and also in parallel with the supply voltage, that is of our 8 volt. So this we are having a supply voltage, and this is our 2 microfarad. So this 8 volt is in parallel with the 3 microfarad. So ideally we can say this voltage V, which is our 8 volt, will be somewhere like this, and same will be for 2 microfarad also. So based on this, we can find out the charge on this 3 microfarad. So we can say charge on 3 microfarad, let us call that Q3. So we can say our Q3 will be equal to our 3 multiplied by 8, which gives us 24 microcoulomb. So this is the charge on the 3 microfarad capacitor. Okay. And this indirectly, this charge Q3 will be also on this combination. Sorry, it is Q3. Okay. And which will be also, because in series this 4 microfarad and 12 microfarad capacitor in series, so in series the charge will be same. So therefore we are going to have on the 12 microfarad, the charge will be our Q3. So it means this Q3 charge will be in the parallel combination of this 3 as well as 9. Okay, so this is the basic how the charge is going to subdivide it into the these respective capacitors. And so this Q3 charge will be on 3 and 9 microfarad, and it is going to distribute itself with respect to the ratio of their capacitances. So we can say that charge Q3 distributes itself on, we have this as 3 microfarad and 9 microfarad capacitors. 3 microfarad and 9 microfarad. So we are interested in only 9 microfarad capacitor. Okay. So we can say the charge on 9 microfarad, let us call this Q9. Q9 will be equal to total charge multiplied by its capacitance and total capacitance, that is 3 plus 9, and this gives us 18 microcoulomb. And This, like I said, this Q3 charge will be on in series combination of 4 microfarad and 12 microfarad, and series the charge will be same. Therefore, the charge on this 4 microfarad capacitor will be also equal to our Q3. So we can say that charge on 4 microfarad capacitor will be equal to Q3, which comes as our 24 microcoulomb. Now we can find out a total charge Q, which we said is equal to the summation of charge on 4 microfarad and charge on 9 microfarad. Therefore, total charge, which we denoted as Q, which we require to find out, that is Q4 plus Q9, and this is our 18 plus 24 microcoulomb, and we get from here that Q is equal to 42 microcoulomb. Now we can just use the electric intensity formula, because we have charge Q and we know the distance of this particular point, which is suppose given as R. Then the electric field, let's point be P, so we can say electric field at point P will be equal to KQ upon R square. So you can say electric field at point P will be equal to our EP, and is KQ upon R square. K is our constant, which is 1 upon 4 pi epsilon naught, and its value we already know it. This comes as 9 into 10 raised to the power 9. Charge is 42 into 10 raised to the power minus 6, and the distance is our 30 square, so this comes as 30 multiplied by 30. So we get this comes as 9 goes by this 3 and 3, and we are left with 2 zeros, that is our 100, and 100 goes 10 raised to power minus 10, and this is plus 9, so this will be coming as 420 Newton per coulomb. So this is the electric field at point P, which is 429 Newton coulomb. So option number C is the correct one. Option C is correct. Next question. We are given, it was asked in the 2016 main, and it states that the region between two concentric spheres of radii A and B respectively has a volume charge density rho, which is given as A upon R, where A is constant and R is the distance from the center. At the center of the sphere is a point charge Q. The value of A such that the electric field in the region between the spheres will be constant. So we need that the electric field between the spheres is constant. So the electric field here should be constant, or we can say it should be independent of our R. Okay, that is distance. Okay, so electric field should be coming independent of the R. Okay, and we are given, you can say, volume charge density, and the equation for volume charge density is volume charge density, that is given as rho, which is equal to A upon R, and it says that this we have a point charge which is located at the center. So the Q charge is located at the center. So therefore, we can say that using the Gaussian law, so we can say from Gauss law, over a enclosed surface, our E dot A will be equal to charge enclosed and divided by epsilon naught. And here we consider a Gaussian surface whose radius lies between A and B, because we are only interested in the electric field should be. So we consider a Gaussian surface whose radius is suppose given as R, and it lies between this A and B. So it is greater than A but less than B. So you can say considering consider a Gaussian surface of radius R such that this R is greater than A but less than B. Therefore, because it is symmetrical surface, so we can use our this, you can see for the aerial perspective, we can write this as electric field dependent upon R will be our 4 pi R square is equal to, we have our charge enclosed and this charge enclosed with a dependent upon R, and this is equal to epsilon naught. Now let us find out what will be the charge enclosed. Okay, so we are interested in finding out how much charge will be enclosed. Enclosed charge. Enclosed charge within the radius R, that is our Gaussian surface within radius R, and we can write this as our Q enclosed dependent upon R will be equal to total charge that is at the, and this will be between A to B, and this we write for rho R prime and multiply by, this is 4 pi R prime square, and this is derivative of R prime. Okay. And here we have just you can say this, introduce a new variable R prime just to differentiate it with respect to R. Okay, that's the only purpose. And similarly, because we are given the density, charge density, that is rho of R is equal to A upon R. So once again here with respect to R we write R prime, and here also R prime, and substitute in the given equation. So from here we get this as Q enclosed R is equal to charge Q, and this our A to B, and it comes as A upon R prime, and this is our 4 pi R prime square and derivative of R prime, and this our R prime and square goes away. So we are left with only this is our Q plus integration A to B and we have this as A. Let me take out this common. So we can take common as 4 pi A and integration A to B, and here I have this R prime and this as dr prime. Okay, so obviously we are going to get this as, sorry, not A to B, A to R, my mistake, because Gaussian surface is our R. R. So this comes as R prime by 2. So we can write this as Q plus 4 pi A, and this will be equal to our R square by 2 minus A square by 2. Okay, so this is the only purpose of using R prime, because later on it will be directly substituted by R. So in order to avoid the confusion only, we just introduced a variable that is our R prime. Rest it doesn't matter. And now we found out our charge enclosed. Therefore, we can write the equation for our electric field. And electric field was our electric field multiplied by 4 pi R square is equal to, this comes as Q plus 4 pi A. 2 we can take common, so this comes as R square minus A square divided by 2. And here this 2 goes by 4, and we can write this as electric field is equal to 1 upon, yes, I missed one thing, that is 1 upon epsilon naught. So this comes as 4 pi epsilon naught R square, and this is our Q plus 2A R square minus A square. And we can just multiply by A and substitute value of this charge also. So we get our electric field is equal to 1 upon 4 pi epsilon naught R square. So total charge Q will be equal to 2 pi R square multiplied by A, plus we get this as, one second, I made some mistake here. Sorry. Let me, because we have to, okay, we just multiply it and we get this as pi, and this comes as 2 pi A R square. This comes as plus Q minus 2 pi A, and this is A square. And we want that it has to be not dependent upon R. So let us multiply by R square inside, and we get this as electric field is equal to 1 upon 4 pi epsilon naught. And if you multiply by inside R square, we get this as 2 pi A plus this is our Q minus 2 pi A square and divided by R square. And it says that our electric field should be constant, so it should be independent of this R square term. Okay. So we are given that our electric field should be constant. Therefore, we can write that our R square term must cancel out or not be present. Cancel out. Therefore, we can say that this particular section, we can write that q minus 2 pi a square should be equal to 0, because radius cannot be equal to, our denominator cannot be equal to 0, so numerator will be our 0. So from here we can say our what constant a we were supposed to find out. So we can say a will be equal to q upon 2 pi a square. Therefore, option A is the correct one. Option A is correct. Here the only tricky part is that we are given that there is a point charge at the center. Along with that, we are also given that the volume charge density is also our A upon R. So based on this, we found out what will be our enclosed charge. Okay, that is our Q, and according to the Gaussian surface. Based on integration, it comes for the entire surface then. Okay, so this is the important part. Rest is quite simple to solve it. Next question. It was asked in the 2016 advance, and it states that an infinite line charge of uniform electric charge density lambda lies along the axis of an electrically conducting infinite cylinder shell of radius capital R. At a time t is equal to 0, the space inside the cylinder is filled with the material of permittivity epsilon and electrical conductivity sigma. The electrical conduction in the material follows Ohm's law. Which of the following graphs best describe the subsequent variation of the magnitude of the current density at any point in the material? So we have to remember that we have to plot the graph for the current density. And we know that first of all, we are going to find out the electric field, and the electric field when multiplied by the electrical conductivity is indirect, or we can say that Ohm's law is our this current density J is equal to electrical conductivity multiplied by electric field. From there we can easily plot it. So first of all, we are going to find out electric field inside the cylinder. Electric field inside the cylinder. So for that, we are going to use Gauss law. So you can say from Gauss law, we can write that our electric field at a distance small r, which is less than capital R from the axis due to line charge we get this as our electric field, which is dependent upon R, will be equal to our lambda divided by 2 pi r and multiply by epsilon. And this field, if you have to remember, it will be radial in direction and pointing outwards. And in the question it is given that the material behaves, follows the Ohm's law. So we are going to find out the current density from the Ohm's law. Therefore, we can write that current density from Ohm's law, and this gives us that our current density J dependent upon R will be equal to our sigma and our electric field. So this comes as sigma lambda upon 2 pi r multiplied by epsilon. And so this will be our current density from the Ohm's law. Okay. Now it states that as soon as the, you can say, because of this conducting material which is being placed inside the cylinder, the discharging process is going to start. So to remember that as soon as the so we can say discharging process. Can say that as conduction starts, charges starts to move radially outward. Therefore, because of this, you can write that resulting in the current that discharges the line charge. Resulting in a current that discharges the line charge. Discharges the line charge. So it means the current density lambda is going to decrease with time. So you can say line charge density. This means that line charge density, which is given as lambda, decreases with time. So therefore, we can represent our lambda as lambda depending as a time function. And we can say that this lambda as a time function will approach to 0 as our time approaches infinity. Okay. And this, you can say, the discharging of this is exponential, and you can say that the decay is exponential. Decay is exponential. Therefore, we can write the equation that our lambda t will be equal to our lambda naught e raised power minus t upon tau, where this tau is a time constant and that is given as our epsilon divided by the conductivity. Now we can find out our time dependent current density. So you can say time dependent current density we can write, because initially the current density J was only dependent upon the distance, now it is also a time dependent, and this will be equal to our sigma, and this is our 2 pi r multiplied by epsilon only, and we have a time dependent current density. And we substitute value of lambda t we just found out, and this comes as sigma lambda naught divided by 2 pi r epsilon and e raised power minus t upon tau. And this particular value we can call this as maximum current density, and therefore we can write our J dependent upon the distance as well as time is equal to J naught e raised power, we can substitute value of our tau, that comes as now T sigma upon epsilon. And so it means this entire relationship we derived based on the Gaussian law, and where this r is less than our capital R. Okay. Therefore, we can from here we can clearly see that this decay is exponential. You can see this decay is exponential. And it is from maximum value, which is our J naught, so we can just approximately starting from maximum value, and it is going to decay closer to a zero value. Okay. So the correct option, that is our option number D, is the correct option. So this axis will be time and this will be J, which is both radius as well as time dependent. So we can say option D is correct. Option D is correct. Next question. It was asked in the 2016 advance, and it is a passage based question, and it states that consider an evacuated cylinder chamber of height h having rigid conducting plates at the ends and an insulating curved surface as shown in the figure. A number of spherical balls made of lightweight and soft material and coated with conducting materials are placed on the bottom plate. The balls have a radius r which is much smaller than the height h. Now a high voltage HV connected across the conducting plates such that bottom plate is plus V0 and the top plate is minus V0. Due to their conducting surface, the balls will get charge, will become equipotential with the plate and are repelled by it. The balls will eventually collide with the top plate, where their coefficient of restitution can be taken to be 0 due to soft nature of the material of the balls. The electric field in the chamber can be considered to be that of a parallel plate capacitor. Assume that there are no collision between the balls and the interaction between them is negligible, ignore gravity. Based on this, we are given two questions. Okay. Question number 1 as well as question number 2. In question number 1, it states that which of the following statement is correct. So it is about the ball will execute SHM between the two plates, will bounce back from the top carrying the same charge they were bent up. Ball will stuck at the top plate and remain there, and ball will bounce back to the bottom plate carrying opposite charge they went up with. And in part 2, the average current in the steady state registered by the ammeter in the circuit will be. Basic diagram is given to us. We have ammeter and a high voltage, and we have this cylinder in which this curved surface is insulator, and only portion charged is this top as well as bottom plate. And it says that this can behave like a parallel plate capacitor, which is given to us. And the balls are for the initial at the bottom, and it is said that they are going to take the same charge as that of the bottom plate, which is positive in first case. Okay. And as soon as it gets the same charge, they will repel in the upward direction, and rest we are going to discuss how they are going to behave. Okay. So we have to remember that bottom plate is plus V0 and upper plate is our minus V0. So it means because of the bottom plate, let's find out what will be the initial charge acquired by the, you can say, ball. Okay, we can take one ball and the rest of the balls are going to follow the same pattern. We can say initially ball on the bottom plate that is plus V0 and acquires positive charge. So let us assume that charge is our Q1. So we can say our Q1 is equal to 4 pi epsilon R multiplied by our V0. So the force let me write it. You can say force the ball feels let us call that as a F1, which will be equal to Q1 multiplied by electric field, and we can write this will be equal to our Q1, and this is our twice V0 and divided by H. And this force, because it is having the same charge as that of the bottom plate, there will be force of repulsion. So it is going to accelerate upward and hits the top plate. So you can say that it accelerates and accelerate upward and hits the top plate. Top plate. Now the ball is at the top plate and the potential you can see at the top plate is minus V. So you can say at top plate, which is basically minus V0, the ball sticks to the plate, sticks to it. sticks to the plate. And this is because in the question it is given that coefficient of restitution is 0. Coefficient of restitution is given as 0. Yeah, coefficient of restitution is said to be 0. So means now, because of they are going to stick the top plate, they are going to acquire negative charge. So you can see acquires negative charge. Now let us suppose that charge is Q2. So we can say this Q2 will be equal to 4 pi epsilon naught R, and this comes as minus of V naught. Now it is going to force, there will be a force of repulsion between the upper plate and the charge Q2. So it is going to feel the force. So we can say that force on the ball, force on the ball, let us call it as F2, will be equal to our Q2 multiplied by E, and this, the charge is our, you can say this will be our same that of the bottom one but with negative sign. So this comes as minus of Q1, and electric field is our twice V naught multiplied by H. Okay. And it feels force on the ball in downward direction. Okay, so it accelerates downward. It accelerates downward. And therefore this process is going to be continuous. Okay, but in this case the only doubt remains that whether it will be a periodic or SHM. Okay. And here if we try to find out the force and the relationship between the displacement, there is no such relationship. Okay. So we can say that it is periodic motion and not SHM. Periodic motion and not SHM. And therefore it is going to the balls will bounce back and forth from bottom and the top plate carrying the opposite charge, okay, that they went up with. So option number D will be the correct one. So option, the ball will bounce back and forth carrying the opposite charge they went with up. Okay, they are going to get the opposite charge. So option D is the correct one. Option D is correct. Next question, oh sorry, in the part B, in the second part, it states that the average current in the steady state registered by the emitter. Okay, so we have to find out the, and it is proportional to with respect to the voltage. So we know that the bottom and top plate, the potential are, bottom is plus V naught and top is our minus V naught. So this is our minus V naught and this is our plus V naught, and is it connected with a high voltage. Okay, and it's said to behave like a parallel plate capacitor. So we can find out the electric field between the plates. You can say the electric field between the plates between the plates, let us suppose that is given as E, that will be equal to over this distance is over H. So we get this as V naught minus of minus V naught and divided by H, which comes as twice V naught H, okay, which we have used previously also. Now the charge acquired by the ball, okay, so because they are a tiny sphere, so we can say that they are something like a tiny spherical capacitor. Sorry, the ball acts like a tiny sphere when it will be in contact with the conductor. So therefore we can find out its capacitance. So we can say charge acquired by the ball let us suppose that is given as Q. Q will be equal to capacitance of the ball and its voltage, that is our V naught. Okay. Here CB, this is our capacitance of ball, which are tiny spheres. Therefore we can write that our CB will be equal to 4 pi epsilon naught multiplied by R. So therefore we can say charge Q will be equal to, and in this case we are going to assume that in the first case rather, that is it is in the bottom plate. So charge Q, that we just wrote it CB multiplied by V naught, so it comes as our 4 pi epsilon naught R times V naught. Okay. And this we are saying that at bottom plate. Now we can easily find out the force as well as acceleration. So we can say force will be our Q multiplied by E, which also gives us mass into acceleration will be equal to our Q we just found out is our 4 pi epsilon naught R multiplied by V naught, and electric field we also found out is our twice V naught and divided by H. Therefore we can write that our acceleration A will be equal to, this comes as 8 pi epsilon naught R, and we get this as V naught square and mH. Now we can use the equation of the kinematics and find out the time it takes to start from the bottom plate and up till the top plate. Okay. So let us suppose the time is given as T. So we say that time to reach the top plate we can use the equation of kinematics. S is the distance, U will be initial velocity which is 0, so S is equal to ut plus half at square Here S is our h, U is our 0, so we can write our h is equal to half at square, and from here we can write our time t will be equal to 2h divided by a and its square root. We can easily substitute value of our a, and a is our 8 pi epsilon naught r v naught square, and this comes as 2h, and h is multiplied by mh and its square root. So we can further sort it out, and this gives us that this goes by 4, and we can write that time t will be equal to, we get this as m h square and 4 pi epsilon naught r v naught square and its square root. Now we can easily find out the current, average current, okay, because we got the time and we know the charge. So you can say average current I will be equal to charge divided by time. Charge we already found out is our 4 pi epsilon naught r times v naught, and our time is our mh square divided by 4 pi epsilon naught r, and this comes as v naught square and its square root. And we are only interested in the proportionality, rest of thing doesn't matter, because in the question, so in the options we are given that it is proportional to v naught square, v naught, or v naught half, or 0. Okay. So we are interested in our v naught only. So we can say that our current I will be proportional to, in the numerator we have 1 v naught, and in the denominator we have v naught square, but inside the square root. So this automatically comes as v naught square. So current is proportional to v naught square. Average current is proportional to v naught square. That is option A is correct. Option A is correct. Next question. It was asked in the 2017 mains, and it states that an electric dipole has a fixed dipole moment P, which makes an angle theta with respect to x-axis. When subjected to electric field E1, which is in I direction, it experiences a torque T1, that is tau k unit vector. When subjected to an electric field E2, which is given as square root of 3 e j unit vector, it experiences a torque T2, which is negative of T1. Then the angle theta is. So here we are having two electric fields. One is in I direction, another one is j direction. Magnitudes are different, and the torque is the negative of each other. Okay. So we can write the torque due to electric field. Torque due to electric field, and in general we can write that this torque tau will be equal to our dipole moment and cross of the electric field. And in terms of theta, we can write that our this magnetic moment P will be equal to, this will be P, and we have our cos of theta I plus sine of theta j. And we are given, we can divide this question into two parts now, and In the first case, it states that when our electric field E1 is equal to electric field E in I direction, so the torque is given as T1, so T1 will be equal to our magnetic moment multiplied by electric field, which is our E1. So we substitute both values, we get this as our T1 is equal to magnetic moment P, and we have this as cos of theta I plus sine of theta j cross E1 is our EI unit vector. Okay. And this small p is only written to differentiate it from capital P. Okay, this is the only purpose of writing it. Otherwise, this small p is equal to the given dipole moment, that is P. Okay, so it is only minor differentiation, rest calculation will be same. Now if we take the cross product, we can write that our T1 will be equal to, we have this I cross I, which will be coming as 0, and this will be our j cross I, which will be coming as minus. So this comes as minus PE, and here we have sine of theta. Okay. And in the direction, that is our k unit direction. Okay, because minus of k, so this will be k unit direction. And we are given in the question that a T1 is equal to tau k unit vector. Therefore, we can write our tau will be equal to minus PE sine of theta. So this is a small p. So this is the torque in first case. Okay. And this sine can just also that say that this tau will be less than 0 and sine theta will be greater than 0. So therefore theta will be lying somewhere between 0 and 180 degree. Okay. We are going to get the same answer, same conclusion later on also. Now we come to the second part. And second part states that now our electric field is equal to square root of 3 E multiplied by J. Now in this case we are having T2, which will be now our P cross E2. So we get our T2 is equal to, and we substitute the value, we have our P cos of theta I plus sine of theta j, and E2 is our square root of 3 E j unit vector. And we are going to get this as T2 will be equal to square root of 3, this comes as PE and cos of theta, and we are having k unit vector. Okay. And but we are given that our T2 is minus of T1. Okay. So therefore we get that our T2 will be also equal to, that is minus of T1, which we just found out is our minus of minus PE, and this we have sine of theta, and we are having k unit vector, minus minus comes as plus, so this becomes PE sine of theta, and we have k unit vector. So these two are same expression written in a different way, so we can just equate them. Therefore we can say that our square root of 3 PE cos of 60 k unit vector will be equal to our PE sine of theta and k unit vector. So here this PE and unit vector goes away, and we are left with the tangent of theta is equal to square root of 3, which gives us theta is equal to over 60 degree. Okay. This is the same conclusion which we derived from here also. And this comes as B, that is over 60 degree. So option B is correct. Option B is correct. So please keep in mind that this small p which I have written, this small p is same that is given in the question, that is our p. Only to differentiate from this main formula, I have changed it a little bit. Moreover, they cancel out each other, if that doesn't matter. Next question. It was asked in the 2017 mains, and it states that a capacitance of 2 microfarad is required in an electrical circuit across a potential difference of 1 kilovolt. A large number of 1 microfarad capacitors are available which can withstand a potential difference of not more than 300 volt. The minimum number of capacitors required to achieve this is. So we are given that we require a net capacitance should be equal to 2 microfarad and it should be able to withstand a potential difference of 1 kilovolt. But we are given that an individual capacitor of 1 microfarad is available and it can only withstand the potential of 300 volt. Okay, so we have to find the maximum. So basically this is, you can say, a question that is based on the grid of capacitors. So it means capacitor will be connected in series as well as parallels. Okay. So we can just draw an approximate figure, and please keep in mind that all the capacitors are going to have the same value, that is 1 microfarad. Okay. So this is similarly and like by this in the, we are going to get rows and columns, and finally we are going to get the last capacitor. So all these capacitances will be of C1. Similarly in between also. So we can say that these are our n number of capacitors. So this will be our n column, and this will be our m rows, and they will be connected across a potential source, and that potential source will be our 1 kilovolt, that is our 1000 volts. So we are required as per question that the total capacitance of 2 microfarad and withstand a voltage of 1000 volt, and we are given that each capacitor is going to have, suppose, a capacitance of C1, and that C1 is also given to us. C1 is our 1 microfarad, and the voltage, it should be maximum voltage rating, let us suppose that is V1, is also given to us, is our 300 volt. So these are the individual ratings of the capacitor, and total capacitor set net will be equal to 1000, and the capacitance should be 2 microfarad. So first of all, because we are given that each capacitor can only handle only handle 300 volt. So it means in order to withstand this 1000 volt, the capacitors should be connected in series so that the voltage is divided. Because we know the voltage of one capacitor, and therefore we can say that handling voltage rating we know that each capacitor can handle only 300 volt. So therefore the capacitors must be connected in series so that the voltage is divided across them. You can say capacitors should be connected in series so that voltage is divided across them. So that voltage divides across them. So like I said, in series we have n number of capacitors. I can just draw a single chain also. So we are having, these are our n number of capacitors, and they should be bearing a total of 1000 volt. And individual we know is our 300, which is this is our C1 voltage capacity V1. This is also C1 voltage capacity V1, C1, V1, and this is C1 and V1. And this is our V total. So we can say that our V total will be equal to n times V1. So this is our n multiplied by 3000. And we are only going to assume for on the higher side, because once we design for the higher side, lower side can be taken care of. So we can say we want that our V total should be greater than or equal to 1000. So we simply substitute it. We get that our n into 300, sorry, this is 300, n into 300 should be greater than equal to 1000. So from here we get that our n should be greater than equal to 1000/300, and which gives us that our value of n should be our approximately greater than equal to 3.33, and the nearest integer we can say our n is approximately equal to 4. So we have found out that total value of n that will be connected is a 4. Now we can find out the equivalent capacitance of the series group, because we have 4 capacitors that are connected in series. So we can say that equivalent capacitance of series group So we can say 1 upon Cs is equal to, we have 4 capacitors all in series, 1 upon C1, 1 upon C1, 1 upon C1, and 1 upon C1, which comes as 4 upon C1, and C1 is our 1 microfarad. So therefore we get our series equivalent will be equal to 1 upon 4 microfarad. So this is only the series equivalent. Okay. And now we are going to find out the, you can say we found out here only number of columns, and now we are going to find out the number of rows. And here each in terms of decimal, each having a capacitance of 0.25 microfarad. We know that the total capacitance is 2 microfarad. Therefore, we require that each series group should be having 4 capacitance, and it requires our, so we are going to find out now number of these parallel groups, and that we are going to find out based on the our required capacitance. So we can say achieving required capacitance, required capacitance. Obviously now all these CS will be connected in parallel, and parallel we know is a direct summation. So we can say now the C total will be equal to M times our CS, and this comes as our M. CS is 0.25 and C total is our, we know, 2 microfarad. Therefore, we can write that the value of M will be equal to 2.2 by 0.25, which gives us that value of M will be equal to our 8. So we have that we are going to have, this is our 1 CS, and this will be our second CS, and similarly we are going to have final CS, and this number will be about 8. And in each CS we are having 4 capacitors which are connected in series. Therefore the total capacitors in the grid, so you can say total capacitors, total number of capacitors will be equal to M times N, and that is our 8 into 4, which gives us 32. Therefore, option number C is the correct one. Option C is correct. Next question. It was asked in the 2018-17 main, and it states that in the given circuit diagram, when the current reaches steady state in the circuit, the charge on the capacitor of capacitance C will be. Basic circuit is given to us. We are having EMF E. There is a series resistance with EMF, that is our R, a capacitance C, resistance R1, and the resistance R2. And we have to analyze, make analysis of the circuit under the steady state condition, and under steady state the current through the capacitor is equal to 0, or we can say capacitor behaves like a open circuit. So we can say that in steady state, capacitor, in this case C, behaves as an open circuit, behaves as open circuit. So it means no current flows through it. So we can just redraw the circuit, and capacitance open circuit, resistance will be there, but no current will be flowing through it. So this is our EMF E, resistance R, this is our R1, and we are having R2. And let us say that current flowing through here is our I. So same current will be flowing through here also. No current will be flowing through this part. So we can simply use, in order to find out current I, so we can say current I will be equal to E upon R plus R2. This is our current in the circuit. Now we are going to find out the potential drop across R2, and this R2 is in parallel with this entire part. So whatever voltage drop across R2 will be same voltage drop across this part. So you can say that potential drop across R2, potential drop across R2 will be equal to potential drop across capacitor. Drop across capacitor. And please keep in mind that our no current is flowing through the circuit. Circuit means capacitor circuit. In this there is no current. So because of this, the potential drop across R1 will be equal to 0. So entire potential drop will be only across the capacitors. Okay, so we have to remember that also. Indirectly is also true also. Whenever there is open circuit anywhere in the, suppose in your household also, the entire voltage will be found at the point where there is open circuit. Rest of the internal circuitry doesn't matter. Therefore, the potential drop of a capacitor is through R2, it will be our current, that is our I multiplied by R2, and our I we already know. So potential drop of a capacitor, let us call this as VC, and so we can say that our VC will be equal to I multiplied by our R2, which is I, we just wrote it, so this comes as E upon R plus R2 and multiply by R2. And we are supposed to find out the charge. So charge, that is charge across capacitor, will be equal to capacitance multiplied by the voltage across the capacitor. Capacitance is given as C, and this comes as VC, we just found out is our E, and this comes as R plus R2 multiplied by R2. So the option is our B is the correct option. Option B is correct. Next question. It was asked in the 2017 advance, and it states that a point charge plus Q is placed just outside the imaginary hemispherical surface of radius r as shown in the figure. Which of the following statements is or are correct? Okay. So the charge is given as just outside the hemispherical surface, and this hemispherical surface is just like imaginary. Okay, and we have to find out which of this statement is or are correct. So this is basically, you can say, based on the solid angle formula. So let us join this part, and this angle is our theta, and So this hemisphere will be consisting of two parts. One will be this curved surface and another one will be this flat circular surface. Okay, so we are going to have two surfaces on this hemisphere. So we can say hemisphere consists of curved surface and second is our flat circular surface. Flat circular surface. And we have to find out what will be the, basically it's talking about the flux and the electric field component as well as the equipotential surface. Okay. So like I said that there is angle subtended by this flat circular face on this semicircular curved surface is supposed theta. Okay. So therefore we can say that the solid angle subtended by the spherical cap with half angle theta. Okay. That the formula is standard one. So you can say that solid angle subtended by a spherical cap with half angle theta and that solid angle is usually given by this ohmic notation, which is our 2 pi 1 minus cos of theta. Okay. And this value of theta will be obviously 45 because this will be r, this will be r, so theta will be about 45. So here theta is our 45 and we can find out the cos of 45 and cos of 45 is 1 upon square root of 2. So we get this as solid angle will be about 2 pi 1 minus 1 upon square root of 2. Now we have to find, we already know that the relation between the flux and the solid angle, we need to find out rather the relation between flux and the solid angle, and for that we can say that a total flux emitting from the charge q, total flux from charge q, let us call this as phi t, will be equal to our charge upon epsilon naught, and this flux will be uniformly distributed over the entire space which has a solid angle of 4 pi. Okay. So from here we can say that this flux is distributed over entire sphere which has a solid angle 4 pi, which has solid angle 4 pi. Therefore, we can say that a flux through the surface whose solid angle is our omega. We can say that flux through the surface that subtends a solid angle, subtends a solid angle that is our, we can write phi will be equal to our q upon epsilon naught solid angle and divided by total solid angle, that is our 4 pi. And we can also find out the flux through the flat surface and the curved surface, that is our main aim. We can say that flux through the flat surface and which subtends the solid angle, flat surface subtends solid angle, and that angle we just found out is about 2 pi 1 minus 1 upon root 2. So therefore the flat flux leaving the flat surface flux leaving through flat surface, let us call it as phi flat, will be equal to, this is our q upon epsilon naught multiplied by solid angle divided by 4 pi. And now we simply substitute the value, we get phi flat will be equal to q upon epsilon naught multiplied by solid angle we know is our 2 pi, this is 1 minus 1 by root 2 multiplied by 1 upon 4 pi, and here this pi and this goes by 2, so we get our phi flat will be equal to q upon 2 epsilon naught 1 minus 1 upon square root of 2, and we have a hemisphere also, and this forms a, along with the flat surface, it will be constituting a closed surface, and we know because the charge is lying outside the closed surface, so the total flux through the closed surface will be equal to 0. So we can say that since hemisphere plus flat surface, this gives us a closed surface, closed surface. and we are given that charge plus Q lies outside the surface, closed surface. Charge plus Q lies outside the surface. Therefore, total flux through the closed surface is equal to 0. So we can say by Gauss law, total flux will be equal to flux because of the flat plus flux because of the curved, and like I said, this should be equal to 0. So from here we can write that our phi curved is equal to minus of phi flat, and phi flat we know is minus because of negative sign. This comes as 2 epsilon naught, and this comes as 1 minus square root of 2. And so basically it means that the flux entering through the curved surface is equal to the flux leaving the flat surface. This is the basic meaning of that. Sign is negative because of the inward flux and outward flux. And we are also given that all the points on the circumference which is on the edge of the flat surface are equal distance from the charge. So they are going to act as a equipotential surface. Okay. So we can say that all points on the circumference are equal distance from the charge, are equal distance from charge. Therefore, you can say that equipotential So the options that will be the correct one, option number A is the correct, and option number D is correct. So A and D are the correct option. Option A and D are correct. Next question. It was asked in the year 2018 mains, and it states that 3 concentric metal shells A, B and C, respective radii A, B, C, where A, B and C are the given C is the largest one, then B, then A, have a surface charge density of plus sigma, minus sigma and plus sigma rho, that is sigma respectively. The potential at B shell is, so we have to find out the potential at the B shell. So we are given three shells. So A will be of the smallest radius. So this is our A. Then we are having B, which is of slightly bigger radius. So this is our B. And we are having C, which is having the largest radius. So this is our C. And their charge densities are given as plus sigma, minus sigma, and last one is also our plus sigma. So this is our A, B, and this is our C. So we know that the charge on a shell is charge density multiplied by 4 pi r square, where r is the radius. You can say charge on each shell and we know the charge q is equal to sigma multiplied by 4 pi r square. We can divide this formula into, we have three shells, so we can say qa will be equal to over plus sigma multiplied by 4 pi a square. B shell will be equal to minus sigma multiplied by 4 pi b square, and C shell is giving a plus sigma multiplied by 4 pi c square. And we are required to find out the potential. Okay. So you can say that potential on a conducting spherical shell. Potential on a conducting spherical shell. And you can say in general, the potential at the surface of a conducting potential on a conducting spherical shell surface. In general, this potential is dependent on both the charges which are inside as well as the charges which are outside. Okay. Potential on the conducting spherical shell surface is due to all charges inside and outside. And this division of the charges which are inside and outside will be dependent upon their respective radius. Okay. So let us write generalized formula. Therefore, we can say that potential at radius r due to charge q at radius capital R. So we can generalize this depending upon the value of radius. In the first case, we say this value of radius is greater than capital R, that is the charge is outside. And second case, we say we have this radius is smaller than capital R, so charge is inside. Sorry, the potential is inside. Potential of the point is inside, which basically not the charge. Charge is at radius capital Q, capital R. So in the first case, we are going to get this as 1 upon 4 pi epsilon naught, and this comes as Q upon small r, And the second case, we get this as 1 upon 4 pi epsilon naught, and this comes as Q upon capital R. And we have to remember that this charge is at radius capital R. Now we are supposed to find out the potential at shell B, whose radius is B. Potential at shell B, radius is our small b. So first of all, let's find out because of the shell A, whose radius is smaller than B. So we can say contribution from shell A. Contribution from shell A, capital A, where this A is less than B. Okay, so it basically means shell A is inside shell B. Shell A is inside shell B. So we can say, so treat the point charge at the center. So treat point charge at center. Therefore, we can say that our VA will be equal to 1 upon 4 pi epsilon naught charge at the center of A divided by radius B. And we get this 1 upon 4 pi epsilon naught. This is a sigma multiplied by 4 pi A square and divided by B. And here this 4 pi cancels out. So we get this will be equal to sigma A square divided by epsilon naught multiplied by B. So this was because of the shell A. And now we come to the shell B, and shell B will be contributing itself. You can say contribution from shell B itself. Let us call that VB. VB will be equal to 1 upon 4 pi epsilon naught charge on B shell and its radius B. So this comes as 1 upon 4 pi epsilon naught. This is minus sigma multiplied by 4 pi B square divided by B. And here 4 pi epsilon naught, B square goes with this square. So we are left with minus sigma B upon epsilon naught. Now we come to the last shell whose radius is greater than B. Contribution from shell C, and radius of C is greater than B. Or we can say that our shell C is outside B. Shell C is outside B, so we can say, so it acts as a shell of radius C producing a constant potential inside. Producing a constant potential inside. Therefore, we can say that our Vc will be equal to 1 upon 4 pi epsilon naught Qc upon C. 1 upon 4 pi epsilon naught, substitute value of Qc, which comes as sigma 4 pi epsilon 4 pi C square upon C. And here also 4 pi C square and C goes away, and we get this as sigma C upon epsilon naught. Net potential will be their algebraic sum. Total potential Vb will be Va plus Vb plus Vc. Now we simply substitute the values. We get our Vb will be equal to sigma A square epsilon B minus sigma B upon epsilon naught plus this is sigma C upon epsilon naught. We can take sigma epsilon naught as common, so we get our Vb is equal to sigma epsilon naught will be common. We can take this will be our A square by B minus B plus C. So the option is our, okay, so this is our option C will be correct one. We can take B as LCM. Option C, B, option C. So let us take this LCM, sigma upon epsilon naught. This comes as A square minus B square upon B plus C. Therefore, option C is correct. Next question. It was asked in the 2018 mains, and it states that a parallel plate capacitor of capacitance 90 picofarad is connected to a battery EMF 20 volt if a dielectric material of dielectric constant K 5 by 3 is inserted between the plates. The magnitude of the induced charge will be. Okay, so we have to find out the charge induced when the dielectric is introduced between the plates. Okay. And we have to remember the battery is still connected with the parallel plate capacitor. Okay. So we can just divide this into two parts. One is our capacitor that is without dielectric connected with a receiver C, and this is our battery V. And in the second case, we have a dielectric and still connected with the battery. Okay, so this is our V. So let us call this as capacitance is C, and the charge here let us suppose is our Q naught. So we can see initial charge which is basically without a dielectric is our Q naught, which is equal to C multiplied by V. Both values are given to us, so we can write our Q naught will be equal to C is our 9 picofarad, 10 to the power minus 12, and voltage is given to us as 20 volt, which comes as 1.8 into 10 to the power minus 9 coulomb. Now we have inserted a dielectric. Let us call this capacitance now as C prime. You can say capacitance with dielectric, capacitance with dielectric. C prime will be equal to dielectric constant and capacitance without dielectric, that is C. Therefore we can say our C prime K is our 5 by 3. This comes as 1.8 into 10 to the power minus 9. So this goes by 0.6 multiplied by 5. So this will be over 3 into 10 to the power minus 9. Sorry, capacitance is different, my mistake. So C prime is our 5 by 3 and we have 92 picofarad. Sorry. So this comes as 150 picofarad. Now we can find out a new charge. Let us suppose this new charge is our Q prime. Okay. So we can say new charge, that is our Q prime, will be equal to C prime multiplied by V. C prime is 150 picofarad, V is our 10 to the power minus 12, and this comes as 20. So we get our Q prime will be equal to, this comes as 3 into 10 to the power minus 9 coulombs. We have to find out the induced charge. So we can say induced charge is the charge, or rather induced charge is the extra charge that appears due to insertion of the dielectric. It means the difference between the two charges. Induced charge is the extra charge that appears due to insertion of dielectric. Due to insertion of dielectric. Insertion of dielectric. So we can say this as Q induced will be equal to Q prime minus Q naught. We substitute the values, we get this as Q induced will be equal to 3 minus 1.4 into 10 to the power minus 9, which gives us 3 minus 1.2 will be over 1.2 nano coulomb. So option number B is the correct option. Option B is correct. Next question. It was asked in the 2018 advance, and it states that an infinitely long thin non-conducting wire is parallel to z-axis and carries a uniform line charge density lambda. It pierces a thin non-conducting spherical shell of radius r in such a way that arc PQ subtends an angle 120 at the center O of the spherical shell, as shown in the figure. The permittivity of the free space is epsilon naught. Which of the following statement is or are true? Basic figure is given to us. We are given that long thin non-conducting wire is parallel to z-axis and carry a uniform charge density lambda. So we have a lambda charge density subtending an angle of 120 at the center O. And we are supposed to find out, these are the four. Two options are related with electric flux and two options are related with the electric field. So let's first of all find out the electric flux, and for that we are going to use the Gauss law. You can say electric flux through the surface. Electric flux through a surface, and for that you can say from Gauss law we can write the flux phi will be equal to charge enclosed divided by epsilon naught. So in order to find out the charge enclosed, we should be able to find out the length of the wire, that is PQ, that is through the sphere, because it is having a charge density of lambda. So we find out that length of the segment wire inside the sphere. Length of segment wire inside the sphere. Total angle is given into 120. So let me draw only the relevant portion. So this have a PQ and total angle is a 120. So this angle will be over 60. Total angle is given to us as 120. And radius is r, and we have a z-axis something like this. Therefore, the length of the segment wire inside the sphere, and we can say our L will be equal to 2r sine of theta by 2. Here theta is 120 and r is our radius. So we substitute value of theta. So we get this as 2r sine of theta is our 120 divided by 2. And this easily goes by 60, so it comes sine 60. Therefore, we can write that our L will be equal to 2r and multiply by root 3 by 2. Here 2 and 2 goes away. So we get this is equal to r square root of 3. Now we found out that this length, which is nothing but our PQ. Charge density is given as lambda, so we can easily find out the total length, total charge enclosed. So we can say enclosed charge let us suppose that is our Q enclosed will be equal to lambda multiplied by L. Length we just found out is our lambda multiplied by r square root of 3. So now by Gauss law, and which gives us that the flux phi will be equal to charge enclosed divided by epsilon naught. Charge enclosed is over lambda r square root of 3 divided by epsilon naught. So therefore the flux through the shell is given by lambda r square root of 3 multiplied by epsilon naught. So option number A is correct. Obviously option number C is incorrect. So because option A is correct. Option A is correct. Now we come to the option B, which states that electric field component is 0 across all the electric field is 0. Z component of electric field is 0. So for that we are going to find out the electric field due to infinite line charge. Electric field due to infinite line charge at a distance r. Distance r. So we can write formula that electric field E of r is equal to lambda divided by 2 pi epsilon r, and we have this is r unit vector, and it is radially outward from the line charge. So we can say radially outward in the perpendicular direction. Perpendicular direction. And in the, you can say, vector form, we can just write it that our electric field R will be equal to lambda upon 2 pi epsilon r unit vector, because we are having a line charge and this is our point and its direction is our r unit vector, whereas our z axis is in this direction. So from here we can say that our r unit vector is perpendicular to our z unit vector. Therefore the z component, which is suppose given as E of z, will be equal to our E and z, which will be equal to 0. So z component is 0. So option number B is correct. And electric field is normal on the spherical shell. So we have to find out option D. Option B is correct first of all. Option B is correct. We come to option D, which states that electric field is normal. Electric field is normal to the electric field is normal to the surface at all the points. Okay, electric field is normal. And here we are given that we are basically a line charge, and line charge is not symmetrical with respect to the circular surface that is given to us. Okay? And therefore electric field will not be normal at all the points of the surface. So we can say that source of line charge, source is line charge. Source is the line charge, and it breaks the spherical symmetry of the body. It breaks the spherical symmetry. Therefore, we can say that our electric field is not normal to the surface at all points. And it's from the reverse we can also make a conclusion based on that, because the electric field will be normal to the surface only if the spherical symmetry is maintained. And spherical symmetry is maintained, one common example is there, when we have a charge, point charge, that is placed inside a spherical shell. Okay, that's a common example, we can take it. So option number D is incorrect. Option D is incorrect. Next question. It was asked in the year 2018 advance, and it states that the electric field E is measured at point P 0, 0D, generated due to a various charge distribution, and dependence of E on D is found to be different for different charge distribution. Column 1 contains different relationship between E and D. Column 2 describes different electric charge distribution along with their location. Match the function in column 1 with the related charge distribution in column 2. So we are given column 1 and column 2, and column 1 gives a relationship between electric field and D, and column 2 tells about the charge distribution. Okay, so in this case we are going to start reverse. We are going to start with column 2 and match it, try to match it with the column 1. And here the point charge is, you can say, 0, 0, D. So we have point P whose coordinate is given as 0, 0, D. Okay. And electric field is according to the charge distribution. So let us start with the first one, that our due to a point charge at the origin. Okay. So you can say point charge at the origin our electric field is given as 1 upon 4 pi epsilon naught, and this is our charge divided by d square. So from here we can say our electric field is directly is proportional to d square. So therefore our P matches with our option C. So we can say our P matches with option C. So P is with C in all the options. Okay, it was quite straightforward. Let's move the next point. We are given a dipole with a point charge and this and minus charge in this, okay, and take 2L this. So let us start with a dipole configuration. Dipole configuration, and because the point is in z direction, so we can say the dipole moment P will be equal to charge Q, and this is 2A, and we have this as z unit direction, and we are given that the charges are also along z. So we are given that plus Q is placed at z is equal to plus A, not plus A, I think both should be L. Charge is placed at plus L, and we have minus Q that is placed at z is equal to minus of L. So this in place of A, we can write this as L. And the point P is at 0, 0, D. So let us find out the electric field due to positive charge. Electric field due to positive charge will be equal to 1 upon 4 pi epsilon naught, and this comes as Q. We have this is D minus, and we have this as L whole square and z vector. Similarly, we can find out for the negative charge, which will be same except the sign. That is 1 upon 4 pi epsilon naught minus Q. This is D plus L and whole square, and we have a z unit vector. And we can find out the net electric field. We can say our E net will be equal to the algebraic sum positive charge plus negative charge. So 1 upon 4 pi epsilon naught we can take as common. Q we can take as also common. So this comes as 1 upon D minus L whole square minus 1 upon D plus L whole square, and we have this as z unit vector. And this can be easily sorted out, and we can write this will be equal to Q upon 4 pi epsilon naught. It will be giving us 4A D divided by D square minus L square and its whole square, and we have a z unit vector. And we know that our dipole moment, that is our P, is equal to 2L multiplied by Q. And we need to, okay, so 1 second, sorry, yes, this is L. So we need here 4L, so we just modify it, and we can say this is our (4LQ) is equal to twice P. Therefore, we can say that our E net is equal to 1 upon 4 pi epsilon naught. This comes as 2P, sorry, here it is P, multiplied by D divided by D square minus L square. Z unit vector. And under the condition that our D is very much larger than L, we can write that of electric field, and that is because of the dipole now, because E net is our nothing but dipole, will be equal to 1 upon 4 pi epsilon naught. We can ignore this L square, this comes at this is square, d4, and this is D comes D cube. So this comes as 2p divided by D cube and Z unit vector. In terms of proportionality, we can say electric field in a dipole is 1 upon D cube. So let us check which of the options. Option number D is the correct option for our Q. So we can say Q matches with D. Next is our line charge coinciding with x-axis uniform lambda. Okay, that is straightforward now. So we have a line charge, and line charge gives us electric field E is equal to 2k lambda upon D. So here electric field is proportional to 1 upon D. And 1 upon D, and the option is R goes with our B. B. And next is our, we are having two infinite wires carrying a uniform linear charge density parallel to x-axis. The one is along y0 zl plus lambda, another one is at y0 z minus l and a charge of minus lambda. Okay, so here we are having two wires, and it is along uniform linear charge density. Okay, let me check any option matches out. So we are having infinite plane charge coinciding with xy plane with uniform. Okay, let's try T. That's the infinite plane sheet. We have infinite sheet, and infinite sheet is our E is equal to sigma upon 2 epsilon naught. It is independent of T. Independent of D. So which means T is our A. Okay. So we found out our P is our C. So P is our C, which are all. Okay. P is our C, and a dipole is our D cube. Q, yeah, dipole is our D cube. So Q is our D. Where is Q is our D? Okay. So this C and D will be incorrect only correct option is our A and this, and T is our A. Okay, so this is also there. We are left with which part? Okay, we are left with R. What is R? R is inversely proportional to 1 by D. R is inversely proportional to 1 by D. So R is our B. R is our B, and so I think option, something else is left. I think all are done. Okay, so we're left with one part. And two infinite wires carrying a uniform linear charge density parallel to x-axis, one along at Z and other one is at minus L. Okay, and charge density lambda. We have to find out how it is going to behave. So let us try for one part, and the second part will be also giving us a same. So we are left with S, and S states that either it will be equal to our B or it will be equal to C. Okay, let's try it. We will try for only one wire, and because it is only proportionality, we can easily deduce for the second. So we are given the wire is from y is equal to infinite. Okay, and the infinite is, let us start with minus L to plus L, and it is parallel to x-axis. So we can say we have a infinite wire, and for the sake of simplicity, let us say this is Z varies from minus L to Z is equal to plus L. I think we can work it around. Yes, so we can do it this way. So we are given for a line charge, and this is T is matching with our A, and for a line charge we have a net electric field, that is our E, will be equal to, because of the first line charge, that is our D minus L minus, and this comes as second line lambda divided by D plus L. Now we can take their LCM. This comes equal to as D square minus L square D plus L minus of D minus L and the common portion we can say this is 2k lambda, and here if you open it, this comes as d and d goes away, so we get this as 2l and divided by d square minus l square, and this is 2k lambda. And we have said that this value of d is very much larger than our L. Therefore, we can write that our electric field E is inversely proportional to d square. Yes. And so therefore, our S is, this T is for our A and S is for our C, and S is for C, C we are, so option number B is correct. Option B is correct. Next question. It was asked in the 2018 advance, and it states that three identical capacitors C1, C2, C3 have a capacitance of 10 microfarad each. They are uncharged initially. They are connected in the circuit as shown in the figure. C1 is then fully charged. C1 is filled completely with a dielectric material of a relative permeability E of R. The cell electromagnetic force, that is EMF, is V0 8 volt. First, the switch S1 is closed while switch S2 is kept open. When the capacitor C3 is fully charged, S1 is opened and S2 is closed simultaneously. When all the capacitors reach equilibrium, the charge on C3 is found to be 5 microfarad. The value of ER is. So we are given, basic figure is given to us. Two switches S1 and S2, capacitor are C1, C2 and C3, and we fill this C1 with a dielectric given as E of R. V0 is the EMF source whose value is our 8 volt. Excuse me. And initially, first time we say switch S1 is closed and capacitor C3 is charged, fully charged. Then S1 is opened, simultaneously S2 is closed, and final charge on C3, because it is going to discharge, it is given as 5 microcoulomb. So let us find out what will be the initial charge on C3. So we can just redraw the figure. So for this figure, we are going to have our switch is closed and S2 is open, so there is no need to draw it. And this is our C3. So charge on C3, let us suppose we call this as Q3, and we have a 8 volt and switch S1 is closed. So therefore we can say charge on C3 which we called as Q3 will be equal to C3 multiplied by V0, and capacitance of 10 microfarad is given or 1 microfarad is given. Anyways, there will be only difference of, I'm not sure. Okay, let's take 10, doesn't matter. So we get this, but then the charge distribution will be a problem. Let me check whether it is 10 or given as 1. This is given 1 microfarad. Wrong. This is 1 microfarad. Anyways, even if it's 10, we can just substitute later on. It's not a big issue. So we have C3, that is 1 microfarad, V0 is our 8. So therefore we get our Q3 will be equal to 1 into 8. So this gives us Q3 is our 8 microcoulomb. Now we come to the second case. As soon as it is charged completely, that is, it is having a charge Q3, switch S1 is opened and now S2 is closed. So we can just draw the figure now. So this is our S2. We have two capacitors and this C1 is having a dielectric inside, E of R, and this is our C2, and we have a capacitor here as this is our C3, and it is given that when equilibrium is reached, the charge on the capacitor C3 is our 5 microcoulomb. Okay, so initial charge was our 8 microcoulomb and final charge on C3 is 5 microcoulomb. And initially both the charge on C1 was 0 and C2 was also equal to 0. So because of conservation of law, we can say that the charge, only the 3 microcoulomb charge will be lost by C3 and which will be coming in C1 and C2, because C1 and C2 are in series, so therefore charge on both will be same. So we can say that conservation of charge Q3, let us call this Q3 as initial, okay, Q3 initial, and Q3 final is given to us. Q3 final is given as 5 microcoulomb. So we can say that Q3 initial will be equal to QC1, because C1 and C2 in series, so we can take any one of the charge here, any of the capacitor rather, and this will be QC1 plus QC3 final. Q3 initial was our 8, QC1 plus 3, so this gives us QC1 will be equal to, sorry, it is 5 not 3, QC5 will be equal to, QC1 will be equal to 3 microcoulomb, which will be same that of our QC2 because both are in series. Now we can easily use KVL in the loop. So we can say KVL in the loop and let us call this as A, B, C, D, A. KVL in loop A, B, C, D, A. And we can write that, let us suppose the charge on this C1 is QC1, so this will be our QC1 divided by C1 multiplied by its relative permittivity plus C2 divided by C2 will be equal to Q3 divided by C3. And this is about 3 microcoulomb, so QC1 we can just take common, so this will be over 3, and this is 1, so it comes as 1 upon epsilon r plus 1 is equal to 5 upon 1. So this comes as 1 upon epsilon r plus 1 is equal to 5 by 3, which gives us 1 upon epsilon r is equal to 5 by 3 minus 1, which comes as 2 by 3. And from here we can say epsilon r is equal to 3 by 2, which comes as 1.5. So of E of r, epsilon value is our 1.5. I don't think that it should be 10. Anyways, even if it 10, still it not going to, because the value of C is automatically going to cancel out, and the only minor difference will be coming that here we are going to have 80 except of 8. That's the only difference. And finally this here also, this will be over 80, and I think it will be a little bit weird then, because it will be coming then 75. 80 minus 5 will be 75. I think it should be 1 then. That does not look, because okay, anyways, so we got our ER is equal to 1.5. Okay, yeah, 1.5. And I think this was the last question. Yes. So these were the questions which we tried to solve. Total 13 questions from 2016, 2 for mains, 2 advanced, 2017, 3 mains, 1 advanced, 2018, 2 mains and 3 advanced. So these were the total 13 questions completed. Thank you.